Okay, good afternoon. I know it's a bit late in the day, so I appreciate your attention for the talk. My name is Lisa Scullion, and I'm an application manager at the Graphene Engineering Innovation Centre at the University of Manchester, affectionately called the Geek, so I will refer to it as the Geek. It is much easier, although a bit sad. And I look after mainly the construction teams and the coatings teams. And I'm going to give you a bit of an overview today about how we use graphene in concrete and other construction materials. Oh, I forgot I had the clicker. I'm going to start with a bit of an overview of graphene. If you know what graphene is already, then apologies, you can just have a little nap while I talk over that. But for anyone who hasn't really had any experience of graphene before, I'm just going to go over the basics. Graphene is essentially carbon. And it's what you would get if you took away a single layer of graphite. So this is your graphite here. It's already a good material. It's a good conductor. It's strong. It's used in lots of applications. And it's made up of just carbon atoms, and each carbon atom is directly bonded to 3 other carbon atoms, which is different from most allotropes of carbon, where carbon is bonded to 4 different things. What happens when you take away this layer? When you peel one layer away, you get very different properties to the bulk material. So your single sheet of graphene behaves very differently. Graphene's always been there, but it was isolated first in Manchester, 2004. And what the scientists did there is they took the graphene, they stripped the graphene off using sticky tape, and they directly measured the mechanical, electrical barrier properties of the material. And that's why Manchester is famous for graphene. So how do we make it? Most graphene is made from graphite, which is mined from all over the world, and that's predominantly the way we get graphene now. And to make it is usually either a physical, mechanical, or a chemical process. Essentially, we're not growing graphene atom by atom, which you can do. It's a very expensive way of growing graphene. For industrial applications like construction, we make graphene from a top-down approach. So we take graphite, we make it smaller and smaller and smaller. How we do that is mechanical exfoliation, or we can use chemical exfoliation. There's lots and lots of different processes to make graphene. And one of the important points here is that not all graphenes are the same. I'm going to go into it in a bit more detail. But how you make the graphene changes its properties. Where your source graphite comes changes its properties, and any kind of chemical residues you might have on that graphene changes its properties. There are other ways to make it, more sustainable ways, which are not produced at the same scale as traditionally mined graphite for graphene. And these include wood char, recycled tires, biomass, recycled plastics, and waste. This is more of an emerging technology. And one of the issues here is that your starting material is different, so it's more difficult to get reproducible graphene from these kind of sources than it is from pure graphite. So they may tend to be stacked differently, or you may get different functionality. And then finally, there's some new ways to make graphene from waste stream gases. So for example, here there's a company who are now making graphene at scale from waste methane. Their product is hydrogen, and their waste product is graphene, so it's actually now a waste product, which makes the whole thing a lot cheaper. So the properties. I think one of the important things to say here is, and I've mentioned it, is that not all graphenes are the same. If you want your graphene here, your beautiful 1-atom thick layer of graphene, you'd have to grow it. You'd have to chemically grow it on a surface. What we use generally for construction projects is called few layer graphene, and this is anywhere between 1 to 10 layers thick, so 10 atoms thick stacked on top of one another. And that still has properties that are graphene-like. Once you start making that thicker, putting more layers on, then it becomes more graphitic, and you start getting more of the properties of the bulk material back. But for this purpose, this is perfectly sufficient, and is the only way you can use graphene cost-effectively, because you couldn't possibly use your pristine graphene, it'd be too expensive. Also, we've got functionalized graphenes. So one of the major functionalized versions that we use is graphene oxide, where we put different oxygen-containing groups onto graphene. And that could be hydroxyls, carboxylic groups, epoxies, a random assortment of, apologies to non-chemists, a random assortment of oxygen groups, and that can help the graphene to interact with whatever you're putting it into, whether that's cement, whether it's a polymer, whether it's a coating, or what have you. You can also reduce this back down to graphene if needed, which has other properties which I won't go into. Essentially, graphene is strong. It's got a huge tensile strength and a huge modulus for its size. It's completely disproportional. It's incredibly conductive. It's one of the most conductive materials ever. Despite what you might see on the internet, it cannot hold a baby elephant. It's not stronger than steel. This is the general fight we have all the time, is because there's lots of sensationalism around graphene, the wonder material. You know, it got a Nobel Prize. Where did it go? Why is no one using it? Essentially, it's taken 20 years from being able to make it at the lab scale, from a few grams, to being able to make it at multi-ton scale. Much like the talk before, anything that's developed at a university, whether it's the electric cement, it has to go through scale-up. And as every graphene manufacturer makes slightly different graphene, we have to make sure that that graphene is reproducible, you're getting the same batch-to-batch variability. All these things have gone into this timeline of why we're only just seeing graphene in actual products now. It's also completely impermeable, which is important for later on. The other misconception about graphene is it's a material that you can make things out of. You can't make anything out of graphene. It's an additive. You always put it in as an additive, very much like you would carbon black or another kind of additive like that. And the starting point for putting graphene into most things is to make a feedstock, whether that's a master batch of extruded polymer pellets, whether it's a formulation for a coating, an admixture. We can put it into different materials, such as rubber. We can put it into batteries because it's very conductive. I will get onto pavements, I promise. It's just background. Printing, it's very conductive. We can print it onto inks, sensors, thermal sensors, pressure sensors, anything like that. Construction, this is a graphene-enhanced concrete parking bay, which is outside our building in Manchester. They let us actually dig up the parking bay in the front of the building and put graphene concrete in, which is very nice. And we put a G on it just in case you weren't sure. And coatings as well. This is my other hat, but certainly some of the coatings we do are for the construction industry. This thing on the left here is a crash barrier that we did a project with National Highways to put a graphene-enhanced coating onto crash barriers at the side of the motorways. We've got some live trials on site down in Scunthorpe. And the idea here is that the graphene provides a really good increase in anti-corrosion properties, so it extends the life of the barrier and means less replacement of barriers. And lastly, before concrete, this is the geek here on the left. We have also got the NGI, which is the National Graphene Institute. We have a huge amount of people working on graphene in Manchester. It's a big deal. And the whole point of the geek, the NGI is where the research happens, so that's the fundamental lab scale, a few grams, in a clean room. The geek is where we try and translate that into real-world situations. So industry comes to us. We're completely industry-led. We don't have any students. We don't do any research. We take the science from the university and we try and put it into real-world products. You've seen this slide a million times today, so I'm not going to go over it. We know what's wrong with concrete, and we know about the CO2, and we know about the cement. I'm not going to bore you again. So what is graphene in concrete? As I said, it's an additive. The key point about using graphene as an additive in concrete is that you use a tiny, tiny amount. It's a very, very small proportion of your material. So you're talking less than 0.1% by weight of your cementitious material, whatever that may be, in your concrete. And the idea is that we can get really increased strengths mechanical properties, barrier properties, all kinds of different properties just from one material. Obviously, people are doing lots of things. We've heard a lot about them today. You know, the electric cements, the basalt work, lots of people are using cement replacement technology. At no point are we saying that graphene is a magical solution. You know, this will sort everything out. It's got to be something that works alongside all of this other innovation and all of this other work that's going on within the industry. It's something that can hopefully work in synergy with those technologies. It's not going to do it on its own. Briefly, the mechanism. It's a physiochemical mechanism. It works on multi-levels. Essentially, what your graphene is tiny flakes all dispersed through your product with a huge surface area. It's like 2,500 meters squared per gram. It's absolutely huge. And sometimes that graphene can be functionalized, whether we've got oxygen groups in it or not. What that does is directly interacts with your cement hydration reaction. It speeds it up, and it regulates and manages that crystal growth. I forgot it was there. I've been looking up there. It's in front of me. I can't actually read that without my glasses on. That's better. Yeah, that's better. So it acts as a nucleator. It's a nucleation effect, but it's also very, very, very strong. So what you get is mechanical reinforcement, as if you were putting in thousands of tiny fibers of fiberglass, polymers, basalt, whatever you want to put in it. It's the same principle for the mechanical reinforcement, but it also directly affects the microstructure of your cement and your concrete. So. The other important point is cracks. I think that's probably more relevant to a pavement audience today. There's a wealth of academic work that shows that graphene can bridge cracks, stop crack propagation, and generally reinforce the concrete material, which in turn leads to more durable concrete, longer lasting structures. If you can see the images here, does this? I'd have to put it on there. So these are just scanning electron microscopy images of a normal Portland cement, which is what we tend to use at the minute while we're developing the technology. And this is how your crystal structure is generated over 7, 15, I don't know why it's 15, not 14, strange. 7, 15, and 28 days. And that's what you would expect your structure to look like. It looks very different when you look at the graphene modified version. And this is at 0.01% weight of graphene. It's a tiny, tiny amount of graphene in there. What you get is this more regulated structure. And that's from that nucleation effect that you have during the cement hydration. It's more, the pore size is more regulated, it's more interlocking, and it's generally more, it's not more dense, it's just more regulated. People do say density, it doesn't quite work like that. But it is more regulated, and that's why we get much better barrier properties, which I'll talk about later. But that also gives you incredible strength increases. So we're looking at increases in compression, tensile, flex, faster curing in general. Most of these strength increases happen early on, within the 3-7 day period. I think I've got a graph of that. So what are the challenges? If graphene's so amazing, why doesn't everyone just go out and buy some graphene and throw it in? And then you've got amazing concrete, because it's really difficult to work with. Graphene it's a nanomaterial, comes in a powdered form. It's a very, very low density powder, so it's a little bit difficult to work with. It doesn't like being in solution. It doesn't like being in water. It doesn't really like being in anything. And once graphene hits a matrix of anything, certainly a highly alkaline, cementitious pore solution, all it wants to do is aggregate, and it wants to go back to being more graphitic, and it clumps together. And that is the reason why lots of people have actually looked at graphene before, early on, maybe when the graphene wasn't such a good grade as well, and they've put it in, they've not seen anything. because it's just agglomerated. So all they've ended up is little dots of graphene spread within the concrete. And you can see that on this. We've seen it too. You can actually physically see it, or you can see it coming out in your bleed water. So what we spent the last 4 years doing at The Geek is looking at different ways to formulate graphene to get it well dispersed, because we know once it's well dispersed, we can get really, really incredible mechanical uplifts. So how do we do it? It's all about processing and formulation. So where you add the graphene in your process, your order of addition, that makes a difference. How you add it in, what medium you add it into, and how you keep it dispersed within solution. As I say, it doesn't like to be in water. It's a flake, it's not spherical. Traditional dispersants don't really work. So there's a bit of wizardry going on, not only a little bit, to get that dispersed. And I think we're almost there with that sort of technology. Lots of people are using it. Some other companies have got their own dispersions or their own ways of getting graphene in. But we certainly, at the university, we're fairly confident we've got a good method of getting it in. What else? Each design's different. If you change, you're using such a tiny amount, so if you change things, if you change your aggregates, you change your sand, you change all your mix parameters, that can affect the graphene as well. Also, which supplier you get your graphene from. Not all graphenes are suitable for all applications, so there's a lot of choice of materials in there as well. Plus, then you've got to look at its interactions with other chemical admixtures, whether there's any negative effects going on there. There's a lot to do, essentially, and there's an awful lot of data to produce before we can be really confident that we have a product that is ready to go. Just very quickly, this is just an example of some of the compression data that we can see for graphene. So this is a typical C35 CEM1 mix, about 320 OPC. Most of the work we've done is on CEM1 systems, and I know from one of the other talks, it's not something we're going to be doing long term, and most people use some kind of cement replacement technology. But for the purposes of getting the system right and getting our formulations right, this is what we've done the bulk of our work with. What we're doing now, we started over the past year, is looking at different systems, so GGBS, looking at different admixtures, looking at different low cement concretes. Essentially what we see is we can get the strength, we can get the 35-day strength, 35 strength early on, almost at 3 days, certainly by 7 days. And we even surpass the design strength of the concrete after 28 days. Most of this strength increase happens at the early stages, as I said, and it does tend to plateau out. And this graph is just showing that if you use different graphene suppliers, you can get different results. So these are 2 different graphene suppliers, the green and the orange. And again, very, very low dosing. And we've incorporated this as a liquid admixture, aqueous admixture. There are other ways. You could put it in as a solid powder. You could blend it in with one of your raw materials. You could put it in the cement. You could put it in the sand. But this is the way we've done this here. And if you just look at that as a percentage, you're looking about easy 20% uplift over 7 days, which kind of plateaus down after 28 days. We've seen much higher results than this. We've seen 80 before. But again, it's dealing with that reproducibility. These are results we're very confident in. We can do this, no problem. Getting the really, really high strengths, we can do, but not reproducibly enough to talk about it at a forum like this. But it's work that's ongoing. All the benefits. The barrier properties is a big one. But graphene is a barrier itself. It's completely impermeable. But what we've done is we've changed that crystal structure and we've regulated that pore structure, and that has allowed us to prevent the ingress of any kind of aqueous products, water, salt water, chloride ions, anything that could deteriorate the concrete, there's a lot of work that shows that we can reduce these depths of ingress over time. And this is, again, a really, really low dose of graphene, 0.01% by weight. And there's a lot of academic work and some industrial work that shows that as well. Another benefit is shrinkage. So we've done quite a lot of shrinkage work as well. And we see, along with the reduced cracking, we see reduced shrinkage with the graphene material. A lot of that work is qualitative, it's quite visual. We're still in the process of getting kind of more quantitative data on the shrinkage, but it's certainly it's a very noticeable effect with the graphene. I haven't covered shrinkage. Other things within construction, so that's the barrier coatings that I talked about. We've also been looking at FRP systems within concrete. We have a whole application area at the Geek, which is looking at graphene-enhanced fiber-reinforced polymers, not the basalt work, but certainly carbon fiber, glass fiber, some natural fibers as well. What we see is if we put the graphene into our epoxy resin systems when we're making our fibers, we see an uplift in mechanical strength too. So we've combined the two, as you do when you're in the university, you put two things together and see what happens. So we've been looking at reinforcing our graphene concrete with graphene reinforced composite material as well. Again, this is just a picture of, this is our site barriers, our coated barriers on the side of the road. You can see the painted, graphene painted ones versus the uncoated, previously galvanized but looking a bit tatty barriers. And then we've also done some work on asphalt. So we did some work with National Highways, I think it was a couple of years ago, up on the A1, some cold in situ recycling of graphene-enhanced bitumen for road surfaces, and that provided a more durable road surface. So again, a living trial. I think just before I kind of conclude as well, where we are with the graphene in construction, particularly in concrete, is there's only so far we can go as a university. Our centre is a pilot centre. We don't do anything on the gram scale. It's all big bucket stuff. But we don't have that input yet from construction in terms of regulations, codes, all these things that we need to think about. If we make graphene concrete and it's so strong that we can take some of the material out, well, we've done it. We've done some big live trials. We've laid a slab. We've taken a third of the material out. So we've laid a much thinner slab at the same strength. How does that work? Can we actually do that in real life? We're lucky we've had some inputs from some companies who are themselves principal contractors, and they've let us make some very, very big living labs of graphene-enhanced concrete. So we have our parking bay, we have a gym floor, we have a big suspended floor down at the Mayfield depot in Manchester, which made the news, you might have seen it. And that's a big suspended graphene-enhanced concrete floor, which is now a roller disco. So it's getting some abuse, it's been rolled over a lot. Again, these are low-risk structures, and we need buy-in from industry to help us do these kind of living lab pours, anything that's low risk or temporary structures. These are the ways we can look at the real-life situation of using graphene concrete. At the same time, in parallel, we're developing the science, and we're getting to grips with the material, and we're finding the best ways of getting the graphene into the systems. I think it was the last talk as well, Philip said, we don't have to sit around and wait for the university technology. We can do things at the same time. And any kind of input we can get from industries to help us drive this forward is what we really need as the university. So in general, the key points from today, I think, is all graphenes are different. There isn't, no one graphene supplier makes a graphene that is suitable for all applications. At the university, we're particularly graphene agnostic in that we will always pick the right graphene for the job. I think that's very important. And it's multifunctional. not just in construction, in other applications as well. In the concrete, you get mechanical strength, you get barrier properties, anti-shrinkage. There's just an array of different things a very, very small amount of material can do. Oh yeah, I said that. And, you know, reduce crack propagation and things like that. We've been doing it for about 4 years. We've got a small team in the GIG who work extensively on this. And it is going very well. We've got some really good results recently. And most of this is driven by CO2 reduction, whether that's taking material out of a pore, so it's less material usage, less cement, or maybe we can take that cement content down, increase the use of different cement replacements by lowering the OPC levels, but getting the strength that we need for any particular pore. And yeah, graphene can go into lots of different things. And that's essentially it. Thank you.
Thank you, Lisa.